Welcome. So yes, our today's speaker is not Cohen. Yeah. Introduce him briefly. So Noy got his PhD in 2016. Camera. I don't have to say that. So from Beersheba under the supervision of Professor Del Botton. Then he switched for postdoc in Caltech in a group of Professor Bhattacharya for 1 year. And in fact, he stayed in California, but he moved a bit to UC Santa Barbara for 2 more years to work in a group of Professor McKing. Yeah. And since 2019, he's been back to Israel, back to Technium, where he's associate professor now, right? Yeah. And so now he will speak about some spider silk. So please, Noy, the floor is yours.
Thank you. So first of all, thank you for having me. It's a pleasure to be here. I'm a big fan of Prague, so I've been here several times. So today I want to talk about a material that fascinated me for the past 6 years or so, right? That's the spider silk. I don't know how many of you are familiar with it, so I'll start with an introduction. Okay. And well, it worked before, so let's see now.
I had to go out of full screen and back.
Out of full screen and back? Oh, there it is. Okay, it's responding in a delay. Well. This worked a second ago, so hold on, let me see, just make sure that this. Okay. All right, well, if the clicker doesn't work, we'll try again with it. Oh. Are we good now? Oh, okay, sorry about that. Okay, so spider silk, if you're not familiar with it, is it's an incredible material. So I'm sure you've all seen the spider web, the famous spider web, and this guy here is just happily weaving a web, completely oblivious to the fact that the fibers that he's weaving they have extraordinary properties. So spider silk fibers are made of a protein-based network, and these materials, they have very high tensile strength. They're extremely tough, they're extremely stiff. And in fact, if we compare the strength to weight ratio of these fibers, it turns out that they can outperform even steel wires, right? So again, strength to weight, right? So if we compare strength to weight of these materials, these fibers, they even outperform steel wires by about a factor of 5. So they're very impressive and they generate a lot of interest in the community. If we take these silk fibers and we subject them to regions of high humidity, it turns out that we're going to see 3 phenomena that are extremely counterintuitive, especially if you've worked on gels. So again, if we take one of these fibers, right, these fibers that you see here, if we take it, we place it in an environment with very high humidity, so we're talking about above 70-75% relative humidity, the first thing we're going to see that the fiber softens by 2 to 3 orders of magnitude in response to a relatively moderate water uptake. So this fiber, about 20% water, give or take 20%, it has a water content of about 20% in its fully swollen state. And it responds by decreasing its stiffness by up to 3 orders of magnitude. So that's pretty incredible. That doesn't happen in every material. The second thing that happens, and this is even a weirder phenomenon, is again, if I have the silk fiber, I subject it to high humidity, water molecules diffuse into the fiber, and the fiber itself, it contracts. So it shortens, right? So even though water diffuses into it, it shortens. It also dilates, but it shortens by as much as 60%. This is often termed as supercontraction. And if you've worked on gels, you know this is extremely counterintuitive. So if you're all familiar with, say, with all of these polyacrylamide beads that we call superabsorbent polymers, we put them in water, they swell by about 100 times. Or if you think of diapers, in which if we subject them to liquid, they swell isotropically. Most of the gels out there, all of the gels that I'm familiar with besides this one, they all swell isotropically. This doesn't. This contracts. This, you can say that it swells, but it contracts and dilates. And the third phenomenon, which is, again, you can argue that this is even more counterintuitive, is that, again, if I have this silk fiber, water molecules diffuse into it, it starts to twist. So there's no torque applied, right? No mechanical torque. It only twists because of water uptake. And this is very strange, right? So let me quantify this and show you some experiments. I got to press this button like an hour in advance. Okay, anyways, so these are some experimental results. The supercontraction effect has been it's well known. It's been investigated through and through. This is a paper that I very much like from 2006. And what they've done in this work is they took a silk fiber and they measured its stiffness and its supercontraction strain as a function of relative humidity. Okay, and they've done that at 3 different temperatures. Let's focus at what happens at 20 degrees C. So what you can see here is that as long as the relative humidity, as long as the ambient, the environment, has a relative humidity of less than 75%, nothing really happens. The stiffness of the fiber is about 10 gigapascals, and the supercontraction strain is, for all intents and purposes, 0. Once I pass the 75% mark, all of a sudden the fiber begins to contract. And it doesn't contract by a little bit, you can see it contracts by a lot. So we see that it contracts by about 60%. And if you look at its stiffness, we can see that it softens from 10 gigapascals up to tens of megapascals, right? So it's a very drastic reduction in stiffness. Okay, so that's the response, that's the supercontraction and the softening. And there was another paper. Okay, there was another paper that came out in 2019, so this is fairly recent. What the researchers did in this work is they took a silk fiber. Again, they came up with a very clever way to kind of measure the twist. This is we'll talk about this in a little bit. But what you can see here, the red curve is the relative humidity. The blue curve is the twist per unit length. And again, what you can see, as long as I'm below about 60, 65, 70% relative humidity, nothing really happens. But once I pass that point, all of a sudden the fiber begins to twist, and it twists by as much as 270 degrees per millimeter. Right. So this is a pretty significant twist. It's not a small twist. This is the same result for spider silk fiber that was retrieved from a different spider species. Right. So this happens throughout to different degrees, to different extents, but it happens to a lot of these, to most of these silk fibers. Okay. And if we're going to talk about fibers, we should also talk about their mechanical response. A little annoying, but so we should also talk about their mechanical response. So if we're going to talk about fibers, practically the only thing you can do with fiber is stretch it uniaxially, right? And so what you see here, this is a stress strain curves of the spider silk fibers. So the way you obtain or you retrieve a spider silk fibers, there are a few ways of doing this. One of the ways that you can get this fiber from the spider is you can put a spider in a box and then just let it weave away, right? So you let it do its thing. It weaves the network, it weaves its spider web, and then you take the silk fiber and then you stretch it. This is typically what we call naturally spun fibers, right? Because the spider weaved them naturally. And naturally spun fibers, they behave in this way, right? So it's kind of this region here. There's variability because this is a biological material, so I guess that's a given, but you could see that this is the response, right? It starts out like this, and then it kind of curves into, this is the curve that you get. And if you're familiar, this is a very, very typical curve for glassy polymers, right? So glassy polymers behave like this. If you take this naturally spun fiber, you put it in a bath, in an aqueous bath, and then you test it in water, you end up with this green curve here. Oh, this is a little smeared here, but you end up with this green curve here. So this is what we call maximum supercontraction, obtained naturally, and we stretch it in water. This curve here, that's a very typical response of rubbers, right? So this is what rubbers do. And if you take this fiber out of the bath and you put it on the table and you let it dehydrate completely after it's dry, and then you test it, you end up with the blue curve, which means again we're back to this kind of typical glassy polymer behavior. Another method of getting a spider silk fiber is what we call forcibly silk. That's where people torture the spiders. They take a spider, they glue it to some sort of a substrate, and then they force the silk fiber out of it, right? So they kind of force the fiber out of it. And it turns out that if you do this, you end up with a fiber with completely different properties, right? So that's the black curve here. This is what we call forcibly silk, and it looks like this. So people realized this, and they said, all right, this is pretty cool. We can actually go ahead and get different properties. We can get fibers with different properties. Can we control this? Can we manipulate this somehow? And in 2012, they came out with a paper that gave us a method to tune the response of the fiber itself. And so what they said is the following. What this paper suggested is it said, let's take a silk fiber, right? Just naturally spun or forcibly silk. We'll put it in water. We'll let it super contract, right? So it shortens by as much as it wants. And then we're going to let it dehydrate, but we dehydrate under tension, right? So we stretch it a little bit. We let it dehydrate under tension. Now, as you can imagine, by doing this, I'm changing the microstructure, right? There's some effects that I'm doing to the microstructure, which I'll show you in a little bit. But essentially, that's effectively what I'm doing. Once the fiber is dry, I can pull it out. I can look at its length in the dry state, so we'll call that LC. LMS is the length of the fiber in the supercontracted state. And then I can define this alpha parameter, which we call the alignment parameter, because it tells me something about the microstructure. And then test it. And you can see that if I do this process, I can end up with a lot of different properties. Typically, if I want toughness, that is to come at the expense of extensibility, right? So I can have fibers that are very extensible, but they're weaker, or fibers that are less extensible, but they're much stronger. So that's kind of the interplay here. Okay, and so when I looked at all of these, I'm a theorist, so we do a lot of theory in my lab. I started thinking about what kind of a microstructure do I need to have? What kind of a microstructure does the spider silk have that can explain all of these phenomena that we're seeing, right? So we're seeing a lot of counterintuitive behaviors. What is it about the microstructure that leads to this? And luckily, there are a lot of characterization papers. There are a lot of experimental papers that use different characterization methods to quantify, to understand the structure of the silk fiber. And so we started going through all of the literature, and this is kind of the picture that we came up with. So when the fiber weaves its web, essentially what it does is it weaves a fiber, a glassy fiber, with an amorphous matrix that comprises polypeptide chains that are highly stretched and highly aligned. And these chains are connected to one another through a series of crystalline domains, right? So these are crystalline domains. The crystalline domains here are stacked beta sheets. But basically, this is kind of a cartoon of what this looks like. Now, if you recall from polymer physics, chains do not like to be stretched, right? A chain never wants to be stretched. Being stretched for a chain is like being in a low entropy or high energy state. So if I had just a standard polymer chain and I were to put it on the table, it would immediately contract because it wants to maximize entropy or alternatively minimize free energy. So chains don't want to be stretched. And in addition, in a network, chains never want to be aligned. If there's no preference, if there's no bias, there's no reason for the chains to be aligned. Yet this microstructure still occupies this configuration, which is energetically unfavorable. And so how does this happen? The way this happens is because each of the chains inside the silk fiber interacts with its neighboring chains through a series of intermolecular bonds, specifically hydrogen bonds. So each chain is connected to its neighbors with a series of hydrogen bonds, and these bonds act as constraints. They're like local constraints that restrict the mobility of the chain. So the chain wants to explore different conformations in space. It wants to kind of wobble around, but these bonds do not let it do that, right? So the chain is pretty much fixed. It's fixed in space. And because of that, that enforces alignment and this configuration of the chains. Okay. What happens when water diffuses into the network? So when water diffuses into the network, the water interacts with the hydrogen bonds and it can dissociate them, it can break them. So a chain which was initially constrained with these intermolecular bonds throughout, once these bonds break, all of a sudden it's free to explore other conformations in space. It can start wobbling around, right? It can try to maximize its entropy or minimize its energy, right, under the new conditions that it's in. And so this is kind of a cartoon to illustrate this. So say we have a chain here. This is, say it's a representative chain inside my silk fiber, and it's interconnected to its neighbors with, in this case, 4 intermolecular hydrogen bonds, right? When water comes in, say I broke this bond here, right? And so now all of this segment here is free to kind of move around. It's free to wobble, to explore other conformations. And because of that, we get the super contraction effect. Right? Because of that, the chain can now contract. It can shorten, and we get we start seeing contraction on the macro scale. In addition, what happens, if I remove these constraints, chains are no longer restricted to orientation. They can now explore other orientations in space. They can start moving around and exploring different orientations in space, which means I'm running over the alignment, right? I'm destroying the alignment. And so the chain itself, ultimately, when I've broken all of the bonds, I'm going to end up with a network that very much resembles a rubbery network with chains that are randomly oriented and uniformly distributed. And all of the chains are essentially random coils. There's nothing that restricts them. They can maximize their entropy in whatever way they want. I should also point out that throughout this process, there's also swelling, right? So swelling basically means water diffuses into the network. I have to somehow increase my volume because water occupies space. And so there's some degree of swelling that happens here. And I would argue if I want to see supercontraction in fibers, I need to make sure that the first and 2 consequences are more dominant than the third. Okay. And so after we had this picture in mind, they said, all right, great. Now let's go to this for all intents and purposes, this is a polymer, right? It's just made of polypeptide chains, but it's a polymer. And so let's see if we can use the standard polymer theories to capture this effect. And so to do this, Okay, and so to do this, well, I'll show you what I've done, but before that, I wasn't really sure how familiar you are with polymer physics. So the most classical model in polymer physics for a chain is what we call the freely jointed chain model, right? And so a freely jointed chain model basically says, let's take a polymer chain and we'll model it as a series of n repeat units. In this case, it's 5, right? So it's 5 repeat units. These are rigid repeat units that are connected to one another in series to form a chain. And then the chain itself will characterize it by the distance between the two ends, right? So the distance between the two ends of the chains, in this case, we call it R, right? And then this is a chain with 5 rigid repeat units or 5 rigid links that are connected to one another. To get the formation out of a chain, what I have to do is I have to take, since these are rigid, the monomers themselves, or the repeat units, I should say, they cannot deform, they're rigid. And so the way to get the formation out of a chain is to have these rotate relative to one another, right? So once these rotate relative to one another, I can increase the distance between the two ends. Okay, so that's pretty much how that works. And back in the 40s and 50s, this was a well-known problem, and people actually were able to compute the entropy of a freely jointed chain. So this is what the entropy looks like. Rho here is basically the distance between the two ends divided by the contour length. So it's some sort of a quantity that's easy to work with. It's constrained between 0 and 1. Tau here is what we call the Langevin equation. And since you know the entropy, you can compute the free energy. And if you know the free energy, you can compute the force. You can compute the force displacement relation. And so this is, in a typical polymer, this is what this is the relation between the force and the end-to-end distance. Right, so that's what it looks like. And if you could see this is pretty trivial, right? So you start stretching, you can see that it's soft, and then the more you stretch, the more it stiffens. And again, this is the same response in rubbers, right? So if you take a rubber, you start stretching it, it's soft. So the more you stretch it, the more it stiffens, right? So this is the classical response of rubbers. If we want to use this theory to characterize the response of silk fibers, though, we got to remember that silk fibers, they have a very different behavior. And so silk fibers, if I want to kind of take this and find the analog, silk fibers have a different microstructure inherently. So they start out in a glassy state. I'm saying glassy, right? In the sense that the chain itself has no conformational freedom. Chains start out as a segment, as a polypeptide segment that has pretty much no conformational freedom. It can't move around and maximize entropy. It's fixed. When water diffuses into the network, all of a sudden the chain starts to gain mobility, right? It starts to get these freely jointed segments along the chain that can occupy different conformations. And so the chain can start moving around, and then ultimately, when enough water diffused into the network, I end up with just a random coil, right? Or something that resembles a random coil. And so, if we want to model this, and we want to use the classical kind of polymer physics theory, we have to somehow input all of this information into a model. And so that is what we've done, right? To model this effect, what we've done is we said, just if you want to model the response of an individual chain, let's look at a chain that is initially highly aligned. It interacts with its neighboring chains through, say, capital M intermolecular bonds. Then we propose a relation that tells me how many bonds the average chain has with its neighboring chains. And that's, of course, it's a function of the relative humidity, and it's a function of it depends on the strength of the hydrogen bonds, or how much energy I need to break the hydrogen bonds. And from this, I can compute the average number of repeat units, and I can compute the entropy. Okay, so when I do this, right, there's a lot of calculations here that I didn't put in, but it's all in the paper, and I'm happy to talk about that after. So once we have all of this, we can actually go ahead and compute the entropy of a chain. We also said that the network is highly aligned, and the alignment gets lost as water diffuses into the network. And so how does that work? To capture this, what we've done is we said, let's define a parameter that's called, we'll call it a degree of orientation. We'll measure it in this way. And this parameter is going to be a function of the relative humidity, such that if I'm below some sort of a critical relative humidity, chains have no entropic freedom, and they're pretty much fixed in space, right? So their orientation is highly aligned. But the more water comes in, the more the chains start to get disoriented, or they start gaining mobility, and the alignment gets lost until ultimately end up with a material that's randomly oriented. So once we had this, we were able to, once we had this, we defined the volume fraction of water molecules. We were able to compute the volumetric deformation, the stress, the stretch of a chain, the fiber stretch. We're able to compute pretty much everything after we had this, right? And then all we had to do was run the calculations and see if this model fits the experimental results. I should also point out, if you take the appropriate limits here, you can also come up with an expression for the Young's modulus. So this is the expression that we got. It's long. but I'll show you it works reasonably well. And I should also point out that again, if you take the appropriate limits here, this recovers the well-known theories of swelling that have been published out there, right? So we're not breaking any math. We were just modifying the existing theories. And so after we had this, we had all of the necessary information. We could go ahead and start comparing this to experimental findings. And so that's what we've done. So what you see here, this is the supercontraction stretch. This is the stiffness as a function of relative humidity. The dots are the experimental results. The curves are the model. And you can see that the model does a pretty good job at fitting this. Now, I should also point out, in the model itself, all of the parameters are physically motivated, right? So we don't have what we don't have the classical fitting parameters. We don't have numbers that we could just kind of throw in there to make it fit. But all of the model parameters are grounded in some physical quantity. So for example, in the model itself, I need to input the dissociation energy of a hydrogen bond. Now, people have actually quantified this using MD simulations, but they quantified this. So there was a paper in 2011 that looked at the energetics of hydrogen bonds in peptide groups. And what they found is that the dissociation energy of hydrogen bonds in a peptide group should range somewhere in the area of 5 to 10 kT, right? So this is kind of the limit that we have to play around with. In addition, if you stretch the fiber to failure, you could look at the maximum extension, and based off of that, you can estimate the number of freely jointed segments. So we've done that as well. To know the maximum volume fraction of water, that's also a quantity that we can estimate, right? So we had a lot of estimations here to kind of see what these properties what these numbers that we plug in need to be. So after we had this, we saw that this worked out pretty well. We compared it to other experimental findings, which I'm not showing here, but yeah. And after we had this, I started thinking, would we be able, if we have this microscopically motivated model, can we say something that is very difficult to measure experimentally, right? So can we give additional insight? Can we say something that it's very hard to measure experimentally, but it would be helpful to kind of understand the system? And I would argue that we can, right? So one of the things that we're saying is we said, if we know that the chain starts out as highly stretched, and as water diffuses into the network, it contracts, right? Let's try to track its contraction, right? Let's see what the end-to-end distance is. Let's see how much it contracts. And so this is one of the kind of simulations that we ran with the model that we had. And what you see is that as long as you're below the critical relative humidity, pretty much nothing happens. Once you pass the critical relative humidity, the distance between the two ends of the chains come closer to each other, right? So the end-to-end distance decreases. And it turns out that a little above 85% relative humidity, the chain starts to stretch a little bit, right? So this was a bit surprising. And it turns out that the reason why we get this stretching here is due to swelling. So in the classical swelling of gels, right? So if I have a gel and it swells, typically the chains in the gel, they have to stretch to make room for the water molecules, right? To accommodate the water molecules that diffuse in. In this region here, I don't have to accommodate them because I'm relieving the constraints on the chains, right? And so I get loss of orientation, I get dilation, but the chain itself contracts. Once I get to this point, I've broken most of the intermolecular bonds that restrict the mobility of the chain. And now the chain starts to stretch a little bit to make room for the water. And we also did a very similar analysis with the orientation, and we can measure how the orientation gets lost. Okay, so based off of this, I hope I've convinced you, we kind of understand why supercontraction happens. So after I had this in mind, after we published this work, we said, we know that these fibers, they also twist, right? So why do they twist, right? Again, this is not a counterintuitive response. Keep in mind, I have a system, water diffuses into it, and it starts to twist. Why would this happen, right? So this is not a trivial effect. And so to understand this, again, we started reading and started looking at the microstructure of this silk fiber. And to understand why this happens, after a lot of thought, we decided that it would be wise to distinguish between different length scales to kind of understand the twist response. And so let me show you what we came up with. So if we start out with the fiber, with the glassy fiber, the spider silk fiber, in the fiber itself, we can define a nanoscale. That nanoscale consists of polypeptide chains and beta sheets. These are typically nanometer length. Right? So you have these beta sheets and you have these polypeptide chains. That's what we call the nanoscale. If we start zooming out, these chains aggregate. They start to aggregate. They interconnect through these intermolecular bonds into what we call nanofibrils, right? So they form nanofibrils, which is somewhat what this blob is supposed to represent. And the beta sheets, they stack to form stacked beta sheets or crystalline domains. And that's one order of magnitude up. Now, it turns out that if you keep zooming out, then these nanofibrils, they're actually connected in series to form helical features. They form some sort of a helical fiber, a helical thread. So it's not a fiber because the whole thing is a fiber, but a helical feature, kind of like a helix along the spider silk fiber, right? So it looks something, this is kind of cartoon, but I hope this demonstrates the point, but it looks kind of like this, right? And this is one scale up. And if I keep zooming out, then I end up with a dragline silk that just has this interconnected and intertwined assembly of polypeptide chains, helical fibers, and so on and so forth. And so this is what happens, right? Now, in the glassy state, we have these helically intertwined fibrillar strands, and keep in mind, this is not an energetically favorable position, configuration, right? The fiber itself doesn't want to be in this configuration because there's energy that's required in maintaining this. And so the way this is maintained is again by these intermolecular bonds. These intermolecular bonds are key to understanding what happens here. They kind of fix the whole structure in space. Once water diffuses into the network, basically the water dissociates the intermolecular bonds. And once these bonds go, nothing maintains this structure. And so what happens is the structure begins to unwind, and that unwinding on the macro scale, we see that as twist. And chains get entropic freedom. And so the entropic freedom, we see that as supercontraction. Right, so these are the two phenomena that we're seeing. So as you can kind of tell, these two happen on different length scales. So basically, if we're thinking again about these length scales, if I want to understand supercontraction, I can shrink myself down to a nanometer scale. I could sit on one of these polypeptide chains, and I'll see the whole environment around me shrinking, right? Because it's an effect that happens at these scales, right? So no matter where I am, I'm going to see a contraction of my environment. However, if I want to see twist, I can't sit on a polypeptide chains. I have to kind of make myself bigger, and I have to look at the helical features. I have to be at an order of magnitude that allows me to see the helical features in the fiber. And only then will I see the surrounding twists. Okay. And so once we have this understanding, we said, all right, so this, we need to model this somehow, right? We need to quantify this somehow so we can say something. And so the way we model this is by doing the following. So this is more of a continuum mechanics-based approach. What we said is let's define three configurations. We'll define a dry glassy state, a hydrated traction-free state, and a hydrated loaded state, right? So these are the three states that I have. And in each of these states, I'm going to quantify the helical feature, the number of turns that I have per unit length on average as alpha naught, alpha SC, and alpha, right? So alpha SC is basically alpha supercontraction, or the number of twists that I have per unit length in the supercontracted state. Now keep in mind, the challenge here is that the traction-free state keeps changing. So this is very similar to problems with growth, right? Or if you're, it's very similar to problems with growth where you have a traction-free state that keeps changing. And I have to somehow account for the fact that the traction-free state changes, this time not with time, but with hydration. And so this is the mapping, right? You can quantify, so this is fairly straightforward. So this is the mapping, the deformation gradient from the glassy state to the traction-free state. This is the mapping from the glassy state to the hydrated loaded state. And once I know the deformation gradients, I can compute the overall deformation gradient from a traction-free state to a loaded state, right? So I can do all of these. And once I have this, if I want to get an expression for the stresses, if I want to be able to solve a boundary value problem, I need a constitutive relation. And so that's the next thing we've done. Now, again, the challenge here goes back to being the fact that the traction-free state keeps changing. We have to account for this somehow, right? So I can, if I just subject this to, if I take this fiber and I put it in water, it's going to change its conformation, even though there's no mechanical forces that are being applied. And so what we've done is we've taken some motivation from liquid crystal elastomers, and we said, let's look at an energy density function that looks like this, right? So this looks like the Neokian. The kind of the twist here is that we're changing the traction-free state. And if you do this, you can define the stress. So that's what the stress looks like. Pi here is what we call, it's the work-less pressure term to enforce incompressibility, because we have to enforce incompressibility somehow. And then you can see if there's no supercontraction, if there's no hydration, I just recover the original Neokian form. In the case of traction-free, in the case of a traction-free setting, where I just take this fiber and I subject it to humidity, then the stretch is just a supercontraction stretch, and the twist is just a supercontraction twist. And if I want to be able to compare this to experimental findings, I need to define relations. I need to prescribe relations for lambda SC and alpha SC. And so that's the next thing we went ahead and did. And so the whole process itself is governed by diffusion. If it's governed by diffusion, that the amount of water that I have in the silk network should scale as the square root of t, give or take, right? So the experiments actually support the square root of t. This is kind of a hallmark of diffusion. And so the K here accounts for the diffusion coefficient, it accounts for the geometry and all of these, all of the diffusion related parameters. And after we had this, we said, okay, so now the supercontraction stretch should look something like this. We assume that it scales linearly with the amount of water in the fiber. The supercontraction, the supercontraction twist also scales linearly with the amount of water in the fiber. And the Young's modulus scales like this. It scales as an inversely proportional to the amount of water. And once we had this in mind, then we were able to kind of define, we were able to talk about boundary value problems, right? Now we have everything we need, so we can define a boundary value problem. So we have this fiber, the fiber is subjected to torsion and a force, or no torsion and no force, or it's subjected to a stretch, right? So whatever we want, we can define it in this way. And we have an expression that relates the force to the stretch, and the torque to the twist, right? IP here is the polar moment of inertia. So once we had this, we said, now we have everything we need. We can go ahead and start comparing to experimental findings. Let's see if this works, right? Let's see if I can use this to capture experimental results. And so we compared it to a wide array of experimental results. Let me show you a few. So again, here, what you see, this is Young's modulus in, as a function of the relative humidity, right? So you can see here, we get a pretty good fit with the trend of the, for the stiffness. In this experiment, what they've done is they took a spider silk fiber, they just held it on one end, no forces applied, they increased relative humidity and saw how it contracts as a function of time. And so again, you can see that we capture this trend. No, this is a function of time now. This is another experiment that was carried out in, it was published in 2009. This experiment is a little more complex. What they've done here is they took a silk fiber, they constrained it on both ends, increased the relative humidity at different rates, and then they measured the stress that develops, right? So I'm holding it, it wants to contract, I'm not letting it contract, it's under tension. And now there's a stress that develops, they measured the stress. And again, they measured it at two different relative humidities or increases of two different rates of relative humidity increase. And again, you can see we get a reasonable fit to these. But the whole reason we came up with this problem was to characterize the twist. And so the next thing is let's characterize the twist. So before I characterize the twist, I have to tell you how they measure the twist. So keep in mind, this is a fiber. The fiber itself has a diameter of micrometers. So it's not like you can draw a line on it and measure how much it twists, right? It's very difficult to see how to actually measure the fact that the fiber twists, just because of the scale of the system. And so in 2017, there was a paper that came out with a pretty clever design of how to measure the twist in these fibers. What they've done is they said, I know the fiber is extremely small. It has a very small radius of micrometers. I'm not going to be able to see twist, right? I don't have the scale to see the twist. And so what they've done is they said, we'll take the fiber, we'll hang a pedal at the bottom, right? So that there was a pedal that weighs about 0.1 grams. It's much heavier than the fiber. And what we're going to do is we're going to increase relative humidity, and we're going to see that we're going to measure how much the pedal twists, right? And based off of the twist of the pedal, we'll be able to say how much the fiber twisted. It's a pretty clever setup. But it does force us to think about the boundary conditions of this problem, right? Because now we have a fiber, the fiber is under a dead load, and we are increasing relative humidity. And so the force is roughly 1 millinewton. The torque is about is 0. There's no torque that's being applied. And the nominal stress, or the dead weight if you want, the dead weight stress is something along the range of 10 to 100 megapascals. It really depends on the radius, and different fibers have different radii, right? So it could be 3 micrometers or it could be 7 micrometers. It could be 10, right? And so once we had this, we said, okay, now we understand what's going on. Let's compare. And so we compared it to the experimental findings. What you see here is the twist per unit length as a function of time for the different fibers that we took, right? So these are 2 different fibers. We can see that the model captures the overall trend. This is a bit of a mishap, which I still don't understand why this happens, but overall the trends we're capturing here, we fit the trend pretty well. And when we submitted this to PRL, we submitted just like this. And then the reviewer asked us, he said, in the experiments, it turns out that the people who conducted the experiments always also measured an elongation of the fiber, right? So the fiber itself, they had this silk fiber, there was a pedal that's on it, maybe there's one. Okay. There was a pedal on it, and it turns out that as the water diffuses into the fiber, we would expect it to supercontract, but it didn't supercontract. It elongated by about 1.5%. And so that forced us to think a little bit. why is it stretching, right? It shouldn't be stretching. And it turns out that the reason why they measured an elongation is because when water diffuses into the fiber wants to supercontract, but it also softens. And there's a weight that's attached to it. And that weight, if the fiber is very stiff, is going to do very little. But if the fiber is very soft, it's going to do a lot, right? And so because of the softening effect, we still end up seeing some sort of an extension here, right? Some sort of a minor extension. And so this kind of forced us to think about this. But after we thought about it, we said, let's plug this into the model and see if our model captures this, because we didn't look at the elongation, the longitudinal elongation until then. And it turns out that our model does a decent job, right? It does capture some sort of an elongation here. You can see here, this is a function of time. We see that the fiber elongates, and the elongation itself is because there is a dead weight, and the softening is much stronger, if you will, than the supercontraction, right? Or the change in stiffness is much more dominant than the supercontraction effect. Okay, so after we had this, we figured, great, now we can understand the twist response. But still, these silk fibers, if I'm going to talk about fibers, typically I'm going to subject them to uniaxial extension. And in fact, I saw the crane exhibit that you have outside, and I saw all of the cranes that I've seen, they took wires, right? They took strings, ropes, to kind of reinforce the structure. So this is actually, these are, if I'm going to use fibers, I'm probably going to test them under uniaxial extension. And so if I want to understand the uniaxial extension response here, the first thing I have to do is look at the trends. What's happening? If I take a silk fiber and I stretch it, what does it behave like? What does it look like? And so it turns out that when you start stretching the fiber, you get this kind of, we call it an elastic region or a linear region, right? So you stretch it initially, there's a linear regime. After the linear regime, it reaches some sort of an yield stress point, and after the yield stress, there's a plateau, there's like a softening effect. And then after the softening, there's the classical stiffening, right? So it stiffens. This again, this is very much resembles, it's very typical of glassy polymers. But I would argue that the mechanisms here are different than the glassy polymers. And so the question is, why is it that this is the trend that we're seeing, right? How do we understand this trend? So after we have kind of an idea of what the microstructure here looks like, I would argue that when we have this spider silk fiber, and we start stretching it, the initial displacement, the chains have very, very little mobility. Chains cannot give me deformation, they're constrained, right? So there's very little that they can actually do. And so when I start stretching the fiber, the way I get deformation is by the distortion of the intermolecular bond. Or in other words, chains can slide past each other. So if I have two chains, right, say I have two chains, and then I start stretching on the macro scale, what's going to happen is these two chains are going to slide past each other because they have no mobility. They don't have a lot of mobility. They can't really move around and give us information. So they slide past each other. But in order to slide past each other, that is a cost. The cost is they have to distort the intermolecular bonds that connect them. So they slide past each other a little bit, and the bonds themselves, they start to distort, right? So I get a distortion of these bonds. When I reach the yield stress, again, what happens is that all of a sudden, all of these bonds have actually reached the maximum stress they can carry, and then they break. And once these intermolecular bonds break, all of a sudden, all of the external load gets transferred to the chains. So what happens, this is a pretty weird situation. We have chains that initially feel very little force, right? We have chains in the initial state. When I start stretching it, the chains don't feel a lot of force because all of the force is carried by the intermolecular bonds. Once these intermolecular bonds go, once they break, all of the external load gets transferred immediately to the chain. And now a chain which was initially under very little force, all of a sudden feels this huge force that's being applied to it. Because of this, chains extend, right? So that gives us this kind of softening or kind of a jump type effect. In addition, I should also point out, and I'm going to show you this in a second, there is evidence that each of these polypeptide chains is what we call intramolecular beta sheets. So these are basically structures that hide some sort of a hidden length that I can break, right? If I break it, then all of a sudden the chain itself extends its contour length. So that's another mechanism that enables me to get a softening effect. And after this point, beyond this point, after the chains found their equilibrium, if I keep stretching, then I just get the classical response from polymer physics. I get entropic stiffening, right? What we call entropic stiffening. I stretch the chains and they stiffen, and I have to again fight against entropy. And so once we had this picture in mind, we said, Wonderful. Let's try the, okay, sorry. And so again, I want to kind of remind you of this experiment that we saw in the first slide before I go into how we model this. And so again, this is one of the experiments that kind of led me to start thinking about this problem. What people have done here is they found some sort of a post-processing that you could do to a silk fiber. They say if I have a silk fiber, I put it in water, I let it super contract, then I dehydrate it under tension. And based off of this process, based off of how much I pre-stretch it before I dehydrate it, I can control its properties. So you can see here that I can get fibers with a wide variety of properties. This all comes out from the same fiber, right? So it's the same fiber, just a different post-treatment. And so this was kind of the main motivations of let's understand why this happened. And so to model this, what we had to do is, so the first thing we had to do was to talk about the orientation of the chains. So essentially what happens if I have a fiber if I have just a silk fiber that the spider gave me, then the chains in this fiber are highly aligned. There's a very distinct ordering of the chains, right? The chains are very highly aligned. When I put it in water, I break these intermolecular bonds. All of the chains start to gain entropic freedom. They start moving around, they gain mobility, and the order gets lost. And I end up with a structure with chains that are randomly oriented and uniformly distributed. If I stretch it and then let it dehydrate, what I'm doing is I'm forcing the structure to find its equilibrium. I'm forcing the bonds, the intermolecular bonds, to form in a situation in which the chains are more stretched. So basically, I'm controlling the alignment of the network. And so to model this, we said, let's define a distribution function. We'll call it rho here, and I'll show you the explicit formulation later on, but this is just as a general sense. We need some sort of an orientation function that tells us that relates the angle between a chain and the end-to-end distance, the probability of having a chain that is a specific orientation to the fiber direction. And this distribution function also needs to be a function of the process that we're doing. How much did we pre-stretch while we dehydrated? And so this is the probability density function. We defined it, and it has to satisfy the state in which if there is no alignment, if it's completely super contracted, then there's no ordering in the system. The next thing we wanted to do, is to model what we call the elastic regime, right? So we want to model what happens in the elastic regime. How does this fiber stretch? And so as we said before, in order for the fiber to stretch, if it starts out like this, right? When I stretch it, basically I'm distorting the bonds. And by distorting the bonds, the chains slide past each other. On the macro scale, I see that as a deformation, right? And again, the deformations in the elastic regime are very small. It's not big. I can't get a lot of deformation out of this. And so what we've done is we said, let's model these bonds as elastic springs, as linear springs. So we model them as linear springs. It looks like this. Delta is the distortion. It's how much the bond moved. KH is what we call the stiffness to distortion. And again, this number we estimated, again, we know what the dissociation energy of intermolecular bonds is supposed to be. It's about 5 to 10 KT. Based off of this number, we can estimate the stiffness. And again, there's quite a range to it. But at least it's an order of magnitude. After we do this, we can compute the energy of the bonds, and then if we differentiate that, we just end up with the elastic stretch, right? So that gives us an idea of what the elastic stress looks like. So that tells us something about the elastic regime. To capture the softening and the stiffening regime, what we've done is we said, okay, so this is the typical chain, right? The typical chain would look something like this. These are stacked beta sheets. These are crystalline domains. These are crystalline domains that nothing will happen to. They're very, very stiff. So this is not one beta sheet, but they're stacked. It's a very strong structure. Inside the chain, there's some evidence. There were papers that reported that there are intramolecular beta sheets. So these are structures that are much weaker. It's a beta sheet, but it's kind of like having a string and you kind of rope it around itself and you interconnect them with a very soft bond. And once the intermolecular bonds break, these chains begin to feel a very strong stretch, very strong force. And because of this force, this structure breaks and the chain elongates, right? So we get this elongation. So if you look at the force displacement curve for a single chain here, it would look something like this. You would have a certain response, just a certain Langevin response or the typical response up to a certain force. At this force, the contour length increases. So you get a jump in the end-to-end distance because the contour length increased. You relieve some of these hidden length. And then you just have a tropic stiffening. And so once you do this, again, it's very easy and straightforward to go ahead and compute the macroscopic response. And so the way we've done this is we came up with an algorithm. It took a while, right? But this is basically, it's an algorithm that enables us to track what happens to the individual chains and integrate over the structure in order to get the macroscopic response. And so once we had this, we figured, right, now we have everything. Let's compare to experimental findings to see if this model works. Okay, and so before we can actually compare it, this is the orientation distribution function that we took. Run through the math, you can find out that this is what the Young's modulus looks like. This is what we assume would be the dependence of the number of intermolecular bonds as a function of the alignment parameter. And once we had all of these, we said that's perfect. Let's compare. And so we started comparing. So what you see here, this is the stiffness as a function of the alignment parameter, right? And so what's happening here is this is the stiffness for a fiber that's super contracted. So if I have a fiber, I put it in water, I take it out, I let it dry without applying any force. I stretch it, I measure its stiffness. This is its stiffness. Keep in mind, in this state, the microstructure of the fiber is just randomly oriented. There's no orientation in the fiber itself, right? So it's randomly oriented, and that is why it's very soft, or relatively soft, right? Again, this is in gigapascals. If I take this fiber in water and then I stretch it and I let it dehydrate under tension, now I've forced a certain ordering in the material, which means that once it's completely dry, I expect to have a fiber that's much stiffer. And it turns out that it is, it's much stiffer, right? So these different curves are for different spider species, right? I'm never going to be able to say the names of these, so I'm not even trying. But you can see we get different spider species, and our model works pretty well with all of them, right? So we can understand what happens to the different fibers. In addition, what we wanted to plot, and what I'm plotting here, is the number of intermolecular bonds that formed between chains as a function of the alignment parameter. And what I'm arguing is that the more I pre-stretch the material and let it dehydrate under tension, the more bonds are going to form. Because I need more agents or bonds to counteract the entropic effects. So if I have a chain and I start stretching it, if I want to keep it stretched, I'm going to need a lot of intermolecular bonds to counteract the entropic forces that want to contract it. So the more I stretch the chain, the more intermolecular bonds I need, or the more constraints I need to maintain this orientation or this conformation. So after we had this, we said, great, now let's compare the experimental findings of stress stretch tests. Sorry. And so what you see here is these are the stress stretch tests, the model on three different materials, or three different silk fibers from different spider species at different relative humidities. So as you can see, the model does a pretty good job at capturing the trends and the overall behaviors that we get. And so when we had this, we were pretty happy. We said, all right, that's pretty good for us. So I want to conclude with this, and then I have a few more minutes that I want to show something else. And so basically, what I've showed you is that we developed microscopically motivated models to understand the behavior of spiders. Additional work that we're doing to understand hysteresis in these fibers, and other types of effects that happen in these in this very interesting material. And yeah. All right. So one more thing I wanted to show you, just a few more minutes and then I'm done. As I wanted to talk about a few other projects that are going on in my lab. So yeah, I'll start with the first one. Okay, so we talked a lot about twist, and back in and this goes back to 2019, I had a postdoc and we started thinking about twist. So if you look at the literature, I haven't found a lot of papers on torsion. Usually when people want to characterize materials, they do either uniaxial extension, biaxial extension, pure shear. Not a lot of torsion out there. But the ones that do report torsion typically say, I have a structure, I apply a torque to it, and in response it twists. Or if I get twist in a different way, like in spider silk, I need to have some either chirality or some sort of an anisotropy, an inherent anisotropy in the material. And we started thinking, would we be able to get a structure that twists in response to not a torque, but in response to something else, a non-torque loading, right? So it could be inflation, it could be extension, anything else. But just using isotropic constituents, right? So I want to take isotropic constituents and I want to construct them in a way that gives me a twist in response to, say, inflation is what I'll show here. But you can also do it in response to other mechanisms. And so the way we've done this is we said, let's say that I have two tubes, right? The blue tube and the green tube. These are Neo-Keen, incompressible, isotropic tubes. What I'm going to do is I'm going to take the blue tube, I'm going to twist it, insert it into the green tube, and then adhere them along the interface, and then let this thing relax into a traction-free state, right? So I end up with this, a traction-free bilayer tube. Essentially what I've done here, this is a traction-free tube, and the two constituents are isotropic. But this structure is going to be loaded with a residual stress. So in a sense, you could say that I've induced, I have stress-induced anisotropy. So it's not material anisotropy. The anisotropy is not associated with the material, but it's associated with the process. So it's a stress-induced anisotropy. And in this structure, because of the residual shear stresses that are stored in it, if I inflate it or stretch it, or if I take the electric elastomers and I apply an electric field to it, this is going to twist. And it's going to twist and it's going to do some interesting things. So what I'm showing you here, I'm going to show you a simulation that we ran on this structure. We've done a lot of different things with this, but I want to show you one simulation, right? So what you see here, this is a tube, and what we're going to do is we're going to inflate it. So this is a bilayer tube. We constructed it in this method, and we're going to inflate it, and I want to show you what it does. Okay, so when we start inflating it, you can see first it twists clockwise, right? At a certain point, I keep inflating it, and then it reverses the direction of twist. Now we twist in the other direction, right? This is very strange. And if I keep inflating it, all of a sudden, it also rotates completely, and now it turns into a different direction from the beginning. Now it rotates clockwise, right? These points are called inversion and perversion, and this is a fascinating phenomenon that happens due to the nonlinear effects of these materials, right? Due to the stiffening effects of these materials. So we published some works on this, which was a very exciting project. The second thing we did has to do with shape morphing structures, right? So this is, again, just a teaser, and I'm happy to talk about this later. But typically today, when we talk about shape morphing, right, we're talking about morphing, having a structure that morphs from one state to another, right? So say I have a plane that deforms into a dome in response to, say, to thermal excitation or electric field or hydration or whatever. We started thinking, would it be possible for me to come up with a design that takes me from configuration A to configuration B to a completely different configuration C in response to the same stimulus, right? So for example, if we think of thermal, which is what we've done here, say I have some sort of a structure, it starts out as a plane, I heat it up, it deforms into a dome, I keep heating it, it deforms into some sort of a wavy surface. So I completely changed the topology. Is this possible, right? Because it's very interesting. And we started playing around with this, and this is what we came up with, right? So this is just the first step, but what we've done is we said, let's look at a bilayer strip, right? So this is just basically what I have here is a bilayer strip. I have two layers, they're glassy, and that's important. They're two glassy layers that are adhered to one another, and what I'm gonna do to these two glassy layers is I'm gonna heat them up. Okay, so these are gonna be struts in a lattice structure, but for now, these are two, just a bilayer. When I heat it up initially, it bends towards this direction, right? Because there is a mismatch between the thermomechanical properties. Now, if I design it correctly, I can get it such that one of the layers is going to transition to rubbery before the other. And by doing this, I can change the relations between the thermomechanical properties, right? So when a glassy polymer transitions to rubbery, its Young's modulus decreases and its CTE increases, right? Its coefficient of thermal expansion increases. And so there's like a mismatch of things that's going on here. And I can get it to transition. If I do it right, I can get it to transition from bending upwards to starting to bend downwards. And we played around with this. We have a lot of different simulations. Let me show you this one. So what you see here is, again, you have this bilayer beam. It essentially initially bends upwards, then it bends downwards, and then it bends upwards again. And these bendings, every time you see a change in the direction, that's because of the glass transition. It's an effect of the glass transition. It's an effect of, it happens because the ratio between the thermomechanical properties changed. After we had this, we used it. So we came up with a theory based on moderate rotations theory, which is kind of like von Karman, but for beams. And we validated, so we 3D printed struts, we validated our theory. And we came up with this very kind of silly illustration that I like to show of a triangle that deforms into kind of a fish shape. We tried to realize this. We're very limited with the materials that we have in my printer. But after we had this, another thing that we started thinking about, and this is something that came out this year, is maybe being able to take this effect and getting structures to transition from non-excitic to excitic. So again, if we think of a lattice structure, say this is my lattice structure, right? And each of the struts in this is an infinite periodic structure or lattice structure. And each of these struts here is made of a bilayer. If I design it correctly, I can set it up so that if I heat it up, it deforms into something like this. And this is an excitic shape. This is in a shape with a negative Poisson ratio. So I can, using this method, I can get structures that transition from acidic to non-acidic based off of temperature. So I can have structures that when I heat them up, all of a sudden they turn into acidic. And I can control the degree of oxidicity. I control how acidic they are by just based off of the properties of the individual layers and the thermomechanical properties. Okay, so with this, I think I talked enough. So I want to thank, of course, my group, all of the people that, all of my group members, past and current, my colleague Klaus, who helped me with some of the spider silk stuff. And yeah, with this, I'll end. Thank you.